Here is the logic board for the HP5360A keyboard for the HP computing counter, and I've just removed the screws holding in the logic board, and you can see at the back here we've got main connector that goes away to the counter. I'm not sure at this stage, I'll have to check the manual, find out what this 36-way connector does. You'll notice there's some screw holes here and here and here. The interconnects going to the board underneath are actually located here, and as you can see there's gold fingers on the board, and these have connectors actually mounted on the board here that's compression type. When you screw down, it should make a good contact. So anyway, there's the actual key switch section of the keyboard, and these key switches are something to behold, even though there's a little bit of discoloration, maybe a minor bit of corrosion on them. I'll just zoom in, see if we can get the focus. There we go. And the keys actually push through the board, and the plunger pushes down. And you can see the action. The spring there makes contact over here. So these things would probably have I'm guessing would have a particularly long life. They are heavy duty, and I don't think they would ever break at all. I may be wrong, but next thing I'll be doing is going around and just checking the continuity of each switch just to make sure they're alright. I'm guessing I won't need to do anything to these. The next step will be to take the keyboard off, because I want to get to the point where I can remove the front panel, which is obviously secured from the inside, so that I can give it a full clean. From the pictures on eBay before I purchased it, it looked like the paintwork had been scratched in multiple places, but it looks like there's only one main spot, so I may not even bother trying to retouch the paintwork. I'll just clean it up and leave that age on the unit. To remove the connections that go between the front panel mounted switches, rotary switch, and any indicators that might be there, there's yet another PCB here with wiring to it, and these compression type connectors, and it's on all four sides, so you can come in top, bottom, and the two sides, so they're quite flexible. If I just zoom out, this now is ready for me to remove the switch section. There's the board there, and that then gets us down to the actual key assembly area, which has these plungers pushing through from the keys. And as you can see too, the casting for this is quite heavy aluminium casting. They really spared no expense in making this thing robust with the computing counter, which was a high-end unit at the time, basically Apollo era electronics. Yeah, it's quite something as just a keyboard really, but it looks like it's built to last forever. While pulling this keyboard apart and just checking everything over, making sure that switches are clean, I was pulling off the status indicator board, and just shows this is really old school digital. Instead of LEDs for status indicators, we have grain of wheat lamps, incandescent lamps. And seeing that I've got this apart, I thought, alright, I'll just do a quick continuity check of the lamps, and found that these two here are open circuit, so we'll have to replace those before I reassemble everything. Yeah, this is super old school, this unit. Also, while going through this, I found that some latching push buttons on the top of the front panel that specify various modes like run, learn, etc. Two were jammed down with a bit of deoxit spray and just a bit of pressure applied. I managed to get those two switches released, and now all the buttons are operating as they should. I'll just swing across here and we can see this is the assembly here. This latching bar was actually frozen in here so that you couldn't actually press one of the other buttons to release the two buttons. So anyway, that's all cleaned up and they're fully operational again, which is good. Well, I've got to have a look to see what I've got in the way of suitable grain of wheat lamps, and we can replace those and I can start reassembling. Okay, I just had a look at the service manual for this keyboard, and these grain of wheat lamps are 5 volts at 50 milliamps, and what's interesting is that they're actually running off of a 15 volt power supply. I don't know the reason for that, but maybe there was the 15 volt supply may not be being used as much and they wanted to shed the load of the lamps to a different supply regulator rather than the 5 volt. But anyway, the upshot is that there's these 150 ohm, look like about 1 or 2 watt resistors that are acting as a current limiter on these lamps, but also to make sure that the lamps aren't over voltaged at all, say in the transition from off to on. They've also got a 5 volt or 5.1 volt Zener diode across the lamp so that the voltage across the lamp won't exceed 5 volts, and when the lamp's fully on, by calculation the volts should come down to about 5.3 anyway. So they've just added a bit of extra protection on those lamps. We've got a 50-year-old set of lamps in there, and as they're only 60 odd cents each, I bought enough so that while I've got the unit apart, I'll completely replace all of the incandescent lamps. I don't want to change these over to LEDs. I could, but I don't really want to. I want to keep it as close to original as I possibly can. Now, what do we need to connect this keyboard to the 5360A computing counter? Well, we need a 50-way Centronics cable that will plug in to the rear of the counter and into the rear of this keyboard. As I didn't have a cable, I had a look into what options I had, and just buying parts, it was going to cost me of the order of $30–40, particularly using a shielded multi-way cable, not just a ribbon cable with IDC type Centronics connectors. So after a little bit of searching, I found that Element 14 had a pre-assembled moulded 50-way Centronics cable, male to male, for about $20, and was really a no-brainer to buy that as opposed to build something myself. And here we go. Let's move that back. There's the cable. This sort of cable also is available on DigiKey. It's quite a decent cable. It's about six foot long, about 2 meters long, and is just ideal for this keyboard. So just a quick example here. We can turn the unit on. We can press external, which allows access to the keyboard. Just press reset, and then say for instance enter 1 2 3, display it, and then enter 3 2 1 and add it, and we've got 444. So just works like a normal reverse Polish calculator. You have in this unit a standard counter with an extension of its accuracy using an interpolation system and a computing engine. And one of the interesting features is that when you select, say, the module or the plug-in selection here, so the module being the 5360A input module or the 5379A time interval module, these units each have a circuit board in them which implements a short program that instructs the computing engine in here how to process the data that's derived from these input units. Just an interesting fact about this unit, it's something that you wouldn't even try to build these days. It has that many ICs in it, it's not funny. Mostly TTL and a few ECL logic chips. But essentially the main counter section and the input module combined, there's 472 ICs. The keyboard has 91 ICs in it, and the plug-in here has 17 ICs in it. So all up as a system, you're running about 580 ICs in the unit, and that just these days is insane. You know, there was no such thing as large-scale integration at the time, or it was the fledgling start of large-scale integration a few years beyond the production of this unit. As the HP computing counter predates Hewlett-Packard's HPIB, or more widely the GPIB interface bus, we see a number of different programming techniques for the counter. Internally, the modules, the input module and the time interval module, each of them provide information back to the counter with an operating program to process that information in particular ways. And as we've seen, also the keyboard is another means of programming the counter. There were three other methods of programming the counter. There was another keyboard, an earlier one, which was an HP5360A, and I've never been able to find an example of that, but it is shown in the training manual for the 5360A. That and the keyboard I have both plug into the external socket on the rear. That same socket can also have plugged into it a programming module which has basically a diode matrix arrangement that allows you to put in programs, hardwired programs, into this unit and then just plug it into the rear of the counter and have a fixed dedicated program. There was also another unit called a 5376A, and that was an actual instrument programmer for the computing counter, and that had quite a bit of extra ability. For instance, the keyboard only allows for you to have a maximum of 32 steps in a given program, whereas the programming unit had a maximum of 200 steps, but you had to switch the base address between a number of base values. That unit also had thumb wheel switches on the front which allow you to enter up to a maximum of 3 constant values as part of the calculation that you're performing. Within the keyboard here there are 3 storage registers, register A, register B and register C. In the computing counter there are working registers X, Y and Z, where X is the main register. The keyboard gives you the ability to view and modify the A, B and C storage registers and the X, Y and Z working registers in the counter. This line of buttons here are register exchange functions. So this one will exchange the contents of register A with register X. This one's B with X, this one's C with X, this one's Z with X, and this one's Y with X. A corresponding set of instructions, which are a copy and shift function that takes register A and places it in X, and then X gets placed into Y. Similarly, there's a function for B, for the C register, for the Z register, and then there is a function that actually is a bit different. It moves the X register into the Y register. And these functions here retain a copy of the data in the original register that is the source. There are two other similar functions here and here. This one is 1xy, where the number 1 is placed in X and X's contents are placed in Y. Similarly, there's a number n here, where n is placed in X and the original contents of X is placed in Y. And n is specified by this switch here, which is the repeat looping switch, and n is set in basically decade values from 1 up to 10,000. So it has 5 positions: 1, 10, 100, 1000 and 10,000. Other functions that are on this keyboard are the if functions, where if X is greater than the contents of register A, then the next step in the program is executed, otherwise that step is skipped. And similarly, if X is less than the register B, then the next step in the program will be executed, otherwise it will be skipped. There are standard functions in this calculator. A standard numeric pad here, which allows you to enter 0 through to 9 with a decimal point. It'll only allow you to enter 1 decimal point. And there are a few additional keys here that allow you to specify various things related to the data entry. Right at the top right here, there is a clear entry button, so you can erase the entry that you're currently entering. There's an enter minus, so you can actually prefix the number you're entering with a minus sign. And then it says here enter prefix, and what that is you'll see additional lettering under each of the numbers on here, and we've got K for kilo, M for mega, G for giga, little m for milli, mu for micro, N for nano, P for pico, F for femto, and T for tera. And what you do is you can enter the scaling prefix in engineering units. You enter this key and then press one of the others to actually scale the number that you're entering. So it has standard arithmetic functions. We've got plus, minus, times and divide. There's also a square root function. Other specialised functions are a multiply by 10, so this is just a single function, but will multiply the contents of the X register by 10, and similarly there's a divide the X register by 10 function. You can clear just the X register, or you can clear all 3 working registers within the counter with this clear button. Down here we have inputs, basically data inputs that can be entered into the program. So module A and module B for the A and B inputs of the main input module on the counter, and then plug in is whatever unit is plugged into the plug-in bay, the data will be returned from the plug-in bay. Other functions are, we've got pause here, it gives you a pause in the program. You can skip a step in the program. At the end of the program you can perform a repeat function, so it just continually repeats. And XFER prog is transfer program, and this allows you to transfer between a main routine and a subroutine, and back from a subroutine to the main routine. The main routine in the case of this keyboard has 16 steps, and the subroutine also has 16 steps. So you can basically have a main routine that calls the subroutine to do a calculation and then come back and display it. And this key here is display X. This will force the X register to be properly displayed on the counter. Other functions on the keyboard here allow you to do things related to programming. Switch here, manual. This just lets the keyboard operate like a manual calculator, no programming in it. There is a learn function here which allows you to enter the steps of your program. There's a step function here which allows you, using the start key, to just do a single step of the program that you currently have loaded. And then the run key here, if you have that depressed and then press start, it will just start executing the program. Switch here has three positions: main, normal and sub. And what that does is, normally you would run in the normal position, but when you're in learn you can actually specifically set main or sub programs, and that way you won't overwrite. For instance, if you use a transfer function, it can potentially, from the main program, it can potentially overwrite a transfer function into the sub program. So if you keep them in the particular either main or sub when you're teaching the unit the program, then you won't have the problem of unnecessarily overwriting locations in one or other of the program sections. HP produced quite a few application notes for the computing counter, giving both the electrical setup and software code for these applications. And just as an example, some of them were peak-to-peak deviation of an FM signal, phase measurement in degrees or radians, electrical length of cables, automatic VCO IC testing, time interval jitter, just to name a few. But today I'll do something far more trivial, and that is set this up as a 1 hour clock. When I had the idea for this, I thought, oh yeah, it should be quite a simple exercise. Well, it wasn't as simple as I thought. Mainly the constraint based on the number of program steps I had, and also how the functions operate, including what registers they destroy when you use particular functions. All of that taken together, it really made me think, test, rethink, rewrite the code quite a few times before I actually got it in a form that firstly would fit within maximum of 32 steps that I have, and two, work in a way that is consistent with the functions that are available in the unit. Okay, the program is loaded. We have a 60 Hz signal coming in here, and we're ready to run. One issue you will note is, because this display has an auto ranging feature, the position of the time will actually move around dependent on what the actual value of time is. So it'll start off just showing seconds over here, then as we get to 1 minute it will actually push the display over and show the 1, and when we get to 10 minutes it'll push it over by another digit, and that's just a function of the operation of the display. So anyway, here we go, we'll start, and it's now counting, and you've got these additional zeros here, but don't worry about that. That's just because we've set it up for a 4-digit display. So it'll just count away there, just count up in seconds, and the algorithm will allow us to get to 59 seconds, and then it will click over, and then it'll start from 1 minute 00. And it's actually amazing that I was able to fit the code in to do what we needed to do, but it does actually work. So here we come, coming up to 57, 8, 9, and then 1, and then the display, as you can see, has moved, and now we've got 2 zeros of the seconds and 1 minute showing here. Coming up to the 10-minute mark, we'll see the display shift again, and in fact it will show a far better representation, because now we see just the seconds and the minutes, even though it's got a decimal point there. But you can see the K enunciator is there, so it's basically 1020 or so.